Okay, hello everyone. So we're going to move into the worksheet number 11 from lecture number 11. So now lecture number 11, we talk about the magnetism. So as we discuss, magnetic field can be created by using magnets. So if you have magnet that point in north south this way, and if I have a magnet south side this way, then these two magnets going to be attract each other. Because of that, there is a magnetic force in between these two, magnetic field in between these two. That's one way that you can create the magnetic field. In addition to that, magnetic field will be able to create by using current carrying wire. This current carrying wire will create the magnetic field around the wire. That will be other way that you can create the magnetic field, right? And so in addition to that, before actually these things, we discuss about the magnetic force, because magnetic force can be created by basically difference two methods, that when we have current carrying wire or when you have charge particles moving, right? So one example that we can say, if I have a current carrying wire inside the magnetic field, say I have magnetic field. So when you bring a current carrying wire to the magnetic field, this wire will feel a force that because of that wire can be bending towards outward or left or right, depend on the magnetic force direction. We use the right hand to find that direction, but that will create the magnetic force that we will be able to calculate by using I and length of the wire, and B and sine of theta. So theta is the angle between your wire, and say this is the current direction, this is the B direction. Theta is the angle between these two, right? So in addition to that, you can have a magnetic field and you can bring a charge particle. If you have a charge particle, if it is moving with some velocity inside the magnetic field, there is a magnetic force on the particle that will be able to calculate by using charge of the particle and velocity B, and again sine of theta. Theta will be again angle between velocity and B in this case, right? To find the direction, we definitely use the right hand. We're going to practice that in here today. Here we calculate the magnetic field on the current carrying wire. We'll be able to use by using constant, that mu naught constant is the permeability that you have the number in the lecture note, divide by 2 pi, and r is the distance from wire to your point of interest, right? So let's move into the question and learn the other stuffs within the questions. Okay, so now let's move into the question number 1. So for magnets, which pole repel each other? So that's the first question, right? So which pole repels each other? If you have a magnet which has north and the other magnet which has the north, you bring the north and north together, we know that they are same poles, they're going to repel each other. And similar to that, if you bring the south and south, also will do the repulsion, right? South and south also will repel each other, right? That's the first question, first part. And now second part is asking which poles attract each other. So that means you should have different pole magnets. That means I have north and south. They're definitely going to attract each other. That means you have the attraction magnetic attraction force, we'll say. Okay, and can you separate poles by cutting the magnet? That is next part. If you watch the lecture part, I explain it. If you have a magnet that has north and south, if I cut into pieces, this each piece as north and south in each piece. What that means is you are not able to separate, not able to separate north from south. They are always staying together. Yeah, because magnetic poles are not monopoles, they are always sitting together, no monopoles. Okay. And number 2, draw magnetic field lines on the bar magnet. Explain what you know about those lines, why it is different from the electric field lines. Okay. Let me take a little more spacing here. Okay, so now, as you guys can see, as I explained in the lecture part, if you have magnet, which is north and south, so magnetic field lines are always circular, right? What are the important properties of magnetic field lines? They are circle around. Circle around. What that means, there is no starting or ending point. No starting or ending point. Starting or ending points. Because you remember that electricity part, we had the ending and starting point. We start from positive charge, ending at negative charge. But magnetism, magnetic field lines, there is no that such a situation. And it's stronger closer to the field. Closer to the poles, actually. Closer to the poles. Those are the properties. And if I draw a magnetic field lines for this one, so you know that you can, it's not allowing me to change the colors. Why? Okay, yeah. So now your magnetic field lines will be going on a circle, something like that, but it is like starting from like north to like south, but they are not actually starting nor ending, they are make a circular loops. Okay. And also you have loops everywhere when you draw it, direction as that. Okay, so now let's move into the number 3. What can you say about the magnetic field lines about a current carrying wire? As I mentioned in earlier, current carrying wire can create the magnetic field line. They will be circle around the wire. As you can see it in here, this is one of the right hand. You're going to point your thumb to the direction of current, and then your fingertips, other 4 fingers, you're going to grab the wire. When you grab the wire, you need to go around the wire. That is the direction of magnetic field. That's why I have magnetic fields like this. And magnetic field will be closer to wire is stronger. When it go away from the wire, they are getting weaker according to the formula. For that, we not I divide by 2 pi, and the R is wherever you are looking at, your point of interest. Okay, so now by keeping those in mind, let's answer this question. What can you say about the magnetic field lines about the current carrying wire? This is another way of creating magnetic line. Yeah, so it will be, you can say it is created around the wire. Okay, so it's right to answer here. And B will be circular around the wire. And also you can say B is decreasing away from the wire. That means it is stronger closer to the wire. Okay, so now draw example. So draw an example. You can draw an example as you want, as I already have it. If you have, since I have upward direction, I'm going to draw downward now. So if I have a current downward direction, you're going to point your thumb to the direction of the current, and then you have the circular kind of magnetic field, but it will be going this way and coming in this way. That is the magnetic field direction. You can draw this one if you want, or you can draw this one, or any other direction. You can do the current to the direction of the right if you want. This is current, and then you point your thumb, and then you have a circular magnetic field going this way and coming out from this way. Whichever one you like, it doesn't matter. And discuss how strength will change when you are moving away from the wire. Actually, we discussed that it is decreasing when you go away from the wire. Okay, so now there is a question. If the current of the wire is 5 amps, calculate magnetic field from 0.5 away from the wire. So now informations are given. I is given, that is 5 amperes, and R, you need to find it 2.5 meters, all are SI units, and that's it we need. And we need the permeability value. As you know, in lecture part you can find it. It is 4 pi times 10 to the negative 7 units Tesla meter over amps. So now we're going to plug into the equation, right? So let's write it in somewhere here. So B equal, I already have the equation here, mu naught I over 2 pi r, that's we're going to use. And mu naught equal 4 pi 10 to the negative 7, and I is 5, and you're going to divide that by 2 pi, and R is 0.50. Okay, let's plug it, and 2 pi will cancel out. Then you can calculate the D. Will be plug into the calculator. I got around 2.0 times 10 to the negative 6 units of Tesla. Okay, so now whichever diagram that you draw, make sure that you make a label, because it does not say which direction the current is. We'll say you're going to use the diagram that you have it in here on the my top diagram. I thumb direction to the current, then your magnetic field lines will be going around. That means in this side it seems like into the board, and this side it seems out to the board. That's the direction of the magnetic field. That means it's going in this direction. This I is the current. Okay, let's label I in blue. Okay. Let's move into number 4. So number 4, we're going to practice the your second right-hand rule. When is the magnetic force act most strong on the current carrying wire? Which formula you use? Explain. Okay, so now you have current carrying wire inside the magnetic field. You remember that we talked about the magnetic force due to current carrying wire equal I, L, B, and sine of theta. Right, so as you can see, magnetic force act most strongly when I is greater, it will be greater. So you can see here, when I greater, F greater, when length greater, F greater, when B greater, F going to be greater, but the maximum happen when theta equal 90 degrees, because when theta equal 90 degrees, sine of 90 will be just 1, right? Because of that, you can get the maximum when the current and the B are perpendicular to each other, right? F is max when theta equal 90. In the other case, when I is max when L is max and when B is max. So these all parameters will affect to the F. Okay. And explain. We explain it. What rule you can use to find the direction of the force? So to find the direction of the force, we're going to use the right hand rule, right? Right hand rule. There is two right hand rules. This is the second one. One is the one that you used earlier to find the direction of the magnetic field. This is to find the direction of the magnetic force when you have current carrying wire or when you have charged particle. Okay. Right hand rule. And do the following example. If I is 5 and B is 0.5, calculate the magnetic force on 0.5 length y. Okay, so now before moving into that, let's see how we use the right hand rule for this example. So I have current to the right direction and magnetic field to the left direction. So you use your fingers as I have it in this diagram and think from your head what will be the direction of the magnetic force. In this case, magnetic force will be pointing outward direction, right? So you're going to do it in yourself, right? So now this is what right? So as we discuss in your lecture part, you know that those fingers will be the direction of magnetic field, B direction, and the thumb of your right hand, this is my right hand, not the left hand, thumb will be the direction of the current in this case, and then your palm going to open to the magnetic force. Those are the three directions that you can show from your right hand, right? So now what you have it on the diagram, take a look on the diagram, you have your magnetic field direction is upward direction and current direction is to the right. So now you need to think how you should keep your hand, right? Again, you practice in your side. This is my right hand, not the left hand, although you see the mirror image. This is my right hand, okay? So you point your fingers to the direction of the B. B is upward. At the same meantime, my thumb should be pointing to the direction of the current. When I do that, you will see that my palm of the hand is going to open towards me, right? That means it is outward from the screen. Okay, so you're going to do it in yourself. Okay, and so now let's go back to the question again. So here you will see that my force direction is to the outward because of that reason. Okay, so now for this problem, your force direction is outward, and I'm going to write it. Force is outward direction. Okay. Outward and inward directions are the directions that you cannot really draw it on the your screen. That's why we use these two symbols. This is outward symbol, right? If something is inward, you need to use this symbol. This is for inward symbol. Okay. Okay, now let's move into this simple question. Okay, so now everything is given in the question. Sorry, let's move into and write down those numbers first. I is 5 amps given, and then B is given 0.5 Tesla, and length is given 0.05 meters. And then we know the mu naught value. No, we don't want the mu naught value. We can just plug into the formula. And what is the theta angle in here? They are perpendicular to each other. That means it is 90 degrees, right? So now let's calculate F. F equal I L B sine of theta, and then we're going to plug it. So we have 5 amps, length 0.05, and we have B 0.5, and then sine of 90, just 1, this part is just 1, and then you're going to calculate the F. Calculate it, and I have 125 newtons. And according to the diagram direction, I would say outward direction. Okay, now let's move into the next question. It's similar question, but now instead current, I have velocity. I can use same right-hand rule. Instead current, now thumb will be the velocity direction. So when is the magnetic force act on most strongly on electron? So now let's enter this little bit. So now formula for this, as you guys know, it will be the other formula that we discussed, that will be force equal QVBN sine of theta, right? So again, magnitude will be max, definitely when the charge is max, definitely when the velocity is faster, when the magnetic field is stronger, and also when the theta is 90 degrees. That's where that you can find maximum magnetic force, right? So now, which formula you use, explain it. So we did it, and you can write it in your words, okay? And then what rule can you use to find the direction of the force? That will be again right-hand rule. Okay, right-hand rule, this one. Okay, so in following example, B is pointing, so now talking about the example, you have B is pointing inward and you have velocity to the right direction. And what will be the magnetic force direction? So now we need to find the magnetic force direction in the figure, right? So again, your right hand, and then you're going to use the magnetic field inward and your velocity to the right. Right? So magnetic field inward and velocity to the right. Magnetic field inward, velocity to the right. So my magnetic field inward velocity is my thumb to the right, and then magnetic force will be, see that, upward. My palm is pointing in the upward direction. This will be the direction of the magnetic force. B into the board, thumb to the right direction, and this is where my palm is pointing. Okay, because of that, your answer will be upward direction. So now direction is upward. Direction is upward. I forgot to mention that since it is talking about the electron in here, so that we need to take care. See that electron, right? So I'm going to write in here upward for positive charge, right? Positive instead of sign positive charge. Because your right hand, you always use for the positive charge. If it is a negative charge, you need to switch the direction. That means if you have upward direction, you need to make it opposite. That means downward for the electron, okay? Downward for electron, because electron is the negative charge. So that will be the basically the answer. Other one is for understanding. Okay, so now let's calculate the question answer. So we need to put it into the information. So we have velocity is 5 meters per second, and B is, seems to be 0.60 Tesla, and says it is the electron. That means Q is the charge of the electron, 1.602 times 10 to the negative 19. Not positive, it's negative 19. negative 19 coulombs, right? So now we have everything. Let's plug into the formula. And F equal QVB sine of theta, and theta also we know 90 degrees in this case, right? So now we have 1.602 times 10 to the negative 19 times velocity 5 SI units meters per second, B 0.60 Tesla, and sine of 90. Okay, let's calculate the F will be equal, I have around 4.8 times 10 to the negative 19 meters. Magnetic force will be usually very small value, right? And direction, as we discussed for the example, downward for electron. Okay, let's move to the next question. Magnetic force can change the path of electron beam. Why? Show an example by drawing. So we actually have done the example on the top also, but let's do it again. Because of force change the path of the electron. So why? We definitely know, because of F, right? So F will create perpendicular to V, and V is the velocity, and the magnetic force. Right, so according to that, because the F is totally different direction than the V and than the B, because of that it will create a deflection, or it will create a direction, or the path will be different, right? So example that you can take the same example that we had, or we'll take the different example to make it little different. So we'll say I have magnetic field. You remember that earlier one I have inward, now I'm going to put it into the outward. You have magnetic field outward, and we'll say there is an electron, that means negative charge electron, moving in upward direction of the velocity. Now what will be the direction of force first, right? So now if you think about the direction of the force, what you have to do, you need to, your magnetic field direction is outward. That means I have to keep my hand like this, outward direction, right? Then my velocity is upward direction. Now when you keep that, you will see your palm going to open to the direction of this way, right? So now when it open to the right direction, that will be for the proton. One more time, your magnetic field, not inward right now. Now it is outward. That I mean to focus my four fingers tips into the direction of me. And then your thumb of the hand, right hand, going to point into the upward direction. Then your palm going to open to the right direction. Now, because of that, if it is a proton, that means your direction will be right. But since it is an electron, direction will be now leftward direction. So now direction of the magnetic force in this case is leftward direction, right? So now when this happened, what happened? Because of this velocity and force, they're going to change the direction of the electron, because of the resultant force is the important part of the moving. So when you have two vectors perpendicular to each other, we know that the resultant will be in between. Because of that, this electron will try to travel in this direction. Okay, this is the real direction of the electron after it insert into the magnetic field. That's the example that you can do. You can draw any direction. You can show that the direction of the electron is bending because of the magnetic force. Okay. And so number 7, two straight wires run parallel to each other. I explained this in the class also. Parallel each other, each carrying the current in the same direction. So you have two wires carry the current in the same direction. When they carry the current in the same direction, those wires going to bend each other. This is going to bend this way, this is going to bend this way, because this will create the pulse on this wire, this direction. This will create the pulse on this wire, this direction. Because of that, they're going to bend towards each other. Okay, and now they will attract each other. If they are in opposite direction current, they're going to repel each other. Okay. Okay, so now let's move to number 8. In order to change the magnetic flux through the loop, what would you have to do? Which law you're using here? So magnetic flux is defined it as how many magnetic field lines can cross the some kind of loop, right? We use it. For example, if I use in the loop in here, when I pass the magnetic field lines through the loop, how many number of lines I can pass through the loop? We call it as magnetic flux. That we use the symbol pi b, and we can calculate it by using magnetic field times cross-sectional area times cosine of theta. That means if you have B in this way, A in this way, then angle between these two are theta. Okay, that's the way that you can calculate the magnetic flux. Okay, so this is in order to, what would you have to do, right? So now if I need this one is greater, I definitely can have B greater, A greater, and when theta equals 0, that will give you the maximum flux, right? Make stronger flux when theta equals 0. You can write it in words, the answer. And which law you use it in here? So which law you use? This is the Faraday's law. Faraday's law is the one that we talk about the change of rate of magnetic flux and the things like that, right? That's Faraday's law. Okay, so last question. If there are three particles travel through the region with the space of the magnetic field into the page. So sometimes people use just a cross or circle with the cross, that is magnetic field inward. And as shown in the figure, what are the sign of the charges of these three particles? So now we need to use the right hand rule, and we need to identify which charge is that. We're going to use right hand rule for the positive charge. Let's use the number 2. So the formula that we have, F equal, we have Q, V, B, sine theta, magnitude wise, right? So now you see that the second particle, I'm going to start with the second particle. Second particle seems to me no bending at all. No bending means there is no pause. No pause means, what is the reason for that? We have velocity, we have magnetic field. There is there is sine theta 90 degrees, but it still force is 0. What is the possibility this particle move on here, right? That means this particle should have charge 0 to make it force 0. That means basically no force for this particle. That means there is the particle, we can call it as neutral. So neutral particle does not change the path when it travels through the magnetic force, magnetic field. No direction of the, no change of direction of the neutral particle. Okay, that means number 2 is a neutral. Okay. And now let's move to the number 1. We'll see what will happen. So now you see that your magnetic field is inward and direction of the velocity is to the right. You turn your fingers inward and rightward thumb, and then you have upward force. So now seems to me like this has upward force. That's why it is moving upward direction. That means this particle is definitely positive charge. Or you can say proton. Okay. Neutral means you can say neutron. Neutron is the neutral particle. And now bottom one, again, you have right hand into the board, come to the right direction and upward, but it seems my particle is going downward than the upward direction. That means this has the downward force. Downward force means basically it is a electron. Okay. So that means here I have third one, negative charge. That means you can say it is a electron. So that's why the beams will change the direction according to the direction of the magnetic force. This is the phenomena that we can have it on your TV and those things, that how we bend the electron beams through the tube. Okay, so let's stop here.